What exactly is a nuclear meltdown? You'll have certainly heard the phrase on TV or in film. It's synonymous with disaster and destruction. But what exactly happens in a meltdown? What causes it, and what are the consequences? Nuclear energy is a highly misunderstood subject. Many TV shows, films, and games have depicted nuclear power, and let me say, the depictions leave much to be desired. The depiction is particularly bad when it comes to nuclear accidents, and in this video, I'm going to clear some things up. We'll get right into it after this. Hello, I'm Dr. Hugh Jones. Before I became a doctor of computer science, I worked as a nuclear engineer. I've worked in the nuclear industry for over a decade, working on projects related to decommissioning, operational maintenance, and radiological safety. Now, I'm not here to tell you whether or not nuclear energy is good or bad. I'm not going to convince you in this video whether the risks of nuclear energy are acceptable or unacceptable. I am here to give you the facts on nuclear accidents in as simple a way as possible and let you make up your own mind. You'll not find the term meltdown in any nuclear textbook. Not because the nuclear industry is trying to cover it up or hide the truth, but the term is far too general for technical use. The term is used in the media as a catch-all term for nuclear accidents. In reality, there are a few different ways a nuclear reactor can have an accident. We'll get into some of those later, but first, we have to talk about how a nuclear reactor works. Most nuclear reactors work in a similar way to a pressure cooker. The cooker in this case, however, contains nuclear fuel. During normal operation, there is a nuclear chain reaction happening inside the fuel. The nuclear chain reaction breaks down larger fuel atoms into smaller products. These smaller atoms are known as fission products and are usually quite radioactive. If the nuclear chain reaction is a fire, the fission products are the ash left over. Both the fission process and the radioactive decay of the fission products release heat. The heat is transferred to the surrounding high-pressure water. The water carries away the heat for electricity generation, but it also performs the important task of cooling the fuel. A constant supply of water must be delivered to the reactor core to cool the fuel, with a series of pumps circulating the water. Now, most nuclear reactors are usually considerably more complicated than this. There are many more components and parts than I'll talk about here, but I have tried to keep it as simple as possible.
No! Who'd have thought a nuclear reactor would be so complicated?
If any kind of problem is detected inside or outside the power plant, then the reactor computer system will automatically shut it down by inserting the control rods. This almost instantly halts the nuclear reaction. However, the danger is not eliminated at this point. The flow of cooling water is needed even when the reactor is shut down. The fuel really is that hot, mainly owing to the decay of radioactive material within. After shutdown, the heat of the fuel reduces quite rapidly. There's a period of about a day or so when the fuel is so hot it could actually cause damage or even melting. Most nuclear accident scenarios involve a loss of this water supply. This could happen in different ways. The piping could break and water could leak out, for example, or power could not be available to drive the pumps circulating the water. What would happen in this situation? Let's take a look at this question by examining what happened at the 3 Mile Island nuclear plant on March the 2nd, 1979. I've tried to simplify the events of the accident as much as possible. The complex sequence of events has been stripped down to focus on what happened rather than the in-depth causes. Now, a problem was detected in the non-nuclear secondary side of the plant. The reactor automatically shut itself down by inserting the control rods into the core, just as it was designed to do. The pumps delivering cooling water to the core continue to do their job, being powered by the connection to the wider grid. However, there was a problem unknown to the operators in the control room. A valve along the pipe delivering water to the core was stuck open, causing it to leak out. This is a classic event in nuclear engineering, and you will find it in any textbook talking about nuclear power. It's called a loss of coolant accident, or LOCA. With the fuel still generating significant heat, the temperature in the water started to rise. Over time, the water level in the core reduced due to the water boiling off as steam. The lowering of the water level started to expose the top of the fuel. This only led to the fuel getting even hotter, but it gets worse. The nuclear fuel itself is encapsulated within a zirconium metal sheath known as the cladding. With the steam all around, the cladding starts to break down, exposing the fuel within. This is the additional consequence of breaking the water, H2O, down into hydrogen, with the remaining oxygen bonding with the metal. It also has an additional consequence of increasing the temperature even further, eventually causing the fuel to melt. Now, anyone familiar with the Hindenburg disaster might have an idea of what the problem is with the buildup of hydrogen. But don't worry just yet. Most of this hydrogen was contained within the reactor pressure vessel, which doesn't contain any oxygen, so it can't burn. Let's zoom back out. So by this point, a significant part of the fuel has melted and formed into a puddle of molten corium at the bottom of the pressure vessel. This is likely where the term meltdown comes from. So do you remember those fission products that are produced from the fission reaction? We mentioned that some of them are radioactive. Now that the fuel and cladding is melting, these fission products are being released into the water remaining in the core. It just so happens that the core is contained within a structure called the containment. The containment is actually designed to keep everything inside in just this situation. With the melting fuel releasing radioactive fission products into the remaining coolant and the leaking valve releasing this water, the containment started to fill up with contaminated water. Within a few hours of the start of the accident, the leaking valve issue was resolved and cooling restored. And to be honest, that's about as bad as this accident actually gets. The containment structure confined the vast majority of the radioactive material, just as it was designed to do. However, some radioactive gases had to be released into the environment, mainly the noble gases xenon and krypton. The release of these gases resulted in a radiation dose to the people surrounding the plant equivalent to a chest X-ray. Consequently, there's no real evidence of any health effects or harm from the accident. Nevertheless, the accident jump-started the anti-nuclear movement, which had no small part in killing the construction of nuclear power plants in the US and abroad. Let's look at another nuclear accident, this one occurring in Fukushima, Japan in 2011. Again, I'm going to massively simplify the events that occurred during this accident to focus on what I consider to be the most important aspects to a member of the public trying to understand the accident. The Fukushima reactors were of a different design to those at 3 Mile Island, but the key aspects are the same. Also, this accident involved 3 co-located reactors, with the accident unfolding slightly differently at each, but I'm going to focus on the factors common to all 3. On March the 11th, an enormously powerful earthquake struck the east coast of Japan. As it was designed to, the reactor detected this and automatically shut itself down. The pumps continued to pump the coolant into the core, cooling the fuel. Things were okay until the tsunami, created by the earthquake, reached the coast off the nuclear power plant. The flooding tidal wave had the consequence of flooding the systems powering the pumps, causing them to fail. Like 3 Mile Island, this resulted in a loss of coolant accident. Again, like 3 Mile Island, the LOCA caused the uncovery of the core, the creation of steam, the breakdown of the cladding, the release of hydrogen, and ultimately the melting of the fuel. Unlike 3 Mile Island, the situation surrounding the power station was incredibly dire. The supply of electricity to the station was entirely cut off in a situation known as a station blackout. The entire region, let alone the power station, was flooded. Some plant workers were even killed by the tsunami. As a result of the dire situation, the duration of the emergency situation and the lack of core cooling was considerably longer. The main consequence of this was the generation of large amounts of hydrogen gas, which ultimately resulted in the explosions. The explosions also had the effect of damaging the containment, meaning that some radioactive materials could escape into the environment. It is likely that the base of the pressure vessel was also breached in at least one of the reactors, releasing the corium onto the base of the containment. Unlike 3 Mile Island, the authorities in Fukushima believe the accident to be serious enough to warrant an evacuation of thousands of nearby residents. Over a decade on from the disaster, there is yet to be any credible evidence of any harm from the radiological release at Fukushima. The only deaths attributable to the accident are those caused by the stress of the evacuations. So with these terrible nuclear accidents, you might be left thinking, why isn't more being done to stop nuclear accidents? Now, as I mentioned earlier, I'm not here to tell you that nuclear power is good or bad or to defend the industry. However, it must be said that an incredible amount is done to minimize the risk of nuclear accidents happening and to limit their harm when they do happen. It's worth mentioning that the reactors involved at both 3 Mile Island and Fukushima were designed in the 1960s and 70s. Since then, both the safety culture within the industry and the design of nuclear power stations have significantly improved. It should be noted that the power stations surrounding Fukushima, some nearer to the epicenter of the earthquake, survived the tsunami and were able to be returned to service in some cases. This is partially due to more significant seawall defences and partially due to more modern waterproofed emergency generators. Some more modern designs have significantly more robust containment structures, such as the EPR being built in the UK at Hinkley Point C currently. This design of reactor has 2 layers of containment, just in case one of them were to fail in an accident, as well as a core catcher below the reactor vessel to catch any corium that should drop out during an accident. Some other designs, such as the AP1000 being built in the US and being considered for the UK, have essentially a swimming pool of water above the core. In the case of a station blackout, the door holding back this water springs open and pours down onto the core, cooling the fuel for up to a day. Some of the so-called small modular reactor designs don't require pumps in an emergency at all, instead relying on natural convection of water around the core. Finally, it is worth mentioning that there are advanced fuels being produced that can't melt, even in the worst case accident scenarios. The cladding or the fuel itself is made from materials that can't melt at the temperatures experienced within the core. I really hope you enjoyed this video on nuclear accidents. So far we've covered 2 accidents that happened in the type of reactor built in the Western world, which rely on ordinary water. I've tried to make it as simple as possible and keep any complex details out. If you are interested in any of the specifics though, please make sure to comment. I'll do my best to answer them, or perhaps I can make another video covering it. I was planning to discuss and explain the big one in this video, Chernobyl, but I've run out of time and I think it warrants a video of its own. The next video in this series will focus on the causes and events of that accident. Make sure to subscribe so you don't miss it. And that's it. Once again, thank you so much for watching. Stay tuned and catch you soon. Bye.